Well, welcome everybody. What are we up to? August 16 in 2026. And I guess officially is this the Drake's Lounge or is this the other one? Anyway, it all kind of becomes the same thing. We're eager to have you here. We've just come off the Eastern Conference out there at Green Bank. And so either you got lots of ideas or you're exhausted. So it could go either way. We have an international crowd here, so we're going to accommodate the folks who are living way off to the east and it's late. I think we often start with Dimitri and then Andy's here and Mark also, if I have everybody over there on that side of the Atlantic. Dimitri, tell us what's been going on. What's new with you, please? Take over.
Hi everybody. Hi, I'm glad to see you all now and was glad to see you at the conference. It was a nice conference. For today, I I have a short message. Just a moment. This is a message about H166 recombination line observation from center of the galaxy Sagittarius A region together with hydrogen nitro and H1 hydrogen observation. This is not first my message about this about recombination line, this recombination line observations. In this in March and February, March and April, but then it was something radio frequency interferences and a real recombination line was not was confused with the peaks, and now I will talk about observation of the June more successful. Two words about Sagittarius A region. This is central Milky Way galaxy with supermassive black hole, about 4 millions of solar mass. Now this is not active galactic nuclear, but was active a bit time ago. Also, we can see traces of their previous activity by in Fermi bubbles in gamma and X-ray emissions. Also, these Fermi bubbles was seen in neutral hydrogen line 21 centimeters. Also, you can see photo of Event Horizon telescope of central black hole. Just a little bit accretion due to you can see and areas of polarization. You can see on this photo. Recombination line they already observed by others professionals. Rather wide in rather wide line, weighs about 13 kilometers per second, and spot on the sky is about 1 degrees. Frequency close to neutral hydrogen pin flip line. So using 20-meter dish L-band receiver in high resolution mode, you can see hydrogen line and this recombination line in one observations. Beat correct system temperature about 93 kelvins it was adjusted. It was adjusted using hydrogen neutral hydrogen line observation due to lab survey data. So I can line from so my system temperature was adjusted for peak of my observed H1 line is about lab survey data about 64 kelvins of brightening temperature. So my previous estimations of system temperature was too high. It was 108 degrees. Now, by calibrating based on lab survey, give a bit lower system temperature. Almost the same spectra in both polarization, X and Y. Polarizations for H1 line was observed in this June. It seems that almost no instrumental polarization effects in 20-meter dish receiver now, and results for recombination line H166α about 0.6, 0.7 Kelvin of peak brightness temperature. It is this expected level, and expected line width about 20, 30 kilometer per second. Minimal theoretical estimations for line width 21 kilometer per second. Contributions from both polarizations are different, more for X polarizations and less low. This must be Y polarizations. Is some type of polarization asymmetry is about 90%, is possibly explained by major amplifications in this line of polarized background from the galaxy center. The sync radiation in background is present. This requires additional confirmations, more observations of say to confirm this line polarizations, and it's very desirable. The polarization calibration of the telescope. I'm planning to perform these calibrations and more observations of this recombination line. This in the next several months. This is all for now. If some questions, I will be glad to answer.
That's neat. You keep exploring new worlds. Thank you, Dimitri. Questions at all?
Not a question, but a comment. This is fascinating. You know, as an astrophotographer, I'm used to taking data at the H alpha line where the electron goes from the energy level 3 to 2 level. What Dimitri is doing is very cool at the 166 alpha transition. For people who are interested, this is a fascinating book about recombination lines for many different recombination lines. And I opened it up, and I mean, it has tables of what you can expect, and including for Dimitri's 166 line. It's really cool stuff. So that's just a comment. Thanks, Dimitri.
Okay, thank you. Okay.
Jack, show us that title again. The book itself.
Sure. It has the exciting title, Radio Recombination Lines by Gordon and Sorencheko or something like that.
Excellent. Thank you.
This is definitely a #1 seller on Amazon.
More questions for Dimitri, please. Excellent. Okay. Well, thank you very much. Well done.
Okay, thank you. Thank you, Ted.
I had one more question.
Adrian.
Yeah. So, Dimitri, I'm not familiar with the statement you had on this last slide. You mentioned major amplification of synchrotron radiation, and I'm not aware of that. Can you explain a little bit of that? I'm familiar with that particular phenomenon.
Okay, this is radiations of in this line. We have polarized background from Sagittarius A regions, and photons from are amplified in the way to us on ionized hydrogen in this line, H166α. This is amplifications. This amplifications due to stimulated radiations of ionized hydrogen. It seems this maser is not saturated, so this radiations is sensitive to level of background and can reflect polarizations, and observing polarizations on this line can give more chance easy to observe polarizations of polarization of background due to maser stimulated amplifications in this line. I hope I answered.
So what you're saying is that the background synchrotron radiation is doing the pumping for the population inversion. Is that basically the concept here?
This is not pumping. This is not pumping. This is seed photons from synchrotron radiations. Pumping is not needed because hydrogen already already excited due to in recombination ladder, but synchrotron background provides only seed for this maser.
Okay, all right. I think you explained it. Thanks a lot.
Okay, thank you.
I think that AI has, through Google, has a good explanation for the synchrotron amplification. So you might look that up, Adrian, and maybe all the rest of us, because I had to, I couldn't. And reading this, I still don't understand it, but interesting. Go ahead.
Okay, Dennis, thank you. Yeah, I'll go back and look that up and see what it has to say. Thank you.
Yeah.
A new opportunity. This is good. Thank you, Dimitri. Excellent as always. The Earth rotates, time zones change, and we're going to work our way over to Andrew, but I think he left us. Oh, there we are, Andrew. Andy, you still there? You've gone dark.
I am, but leave me to the end.
All right. Well, very good. At the very end, we'll see. But we also had Mark. Mark, are you hiding? Yeah, there you are. Mark, come on and tell us what you've been doing.
Yeah, hang on, I'm here. Right. I've been trying to get this SuperSID working, and since some guys suggested to reduce noise, I use the LM7805 to supply the sound card, linear power supply, and keep away from switch mode power supplies. And I managed to get it working yesterday. I'll just explain the difficulty I had. Previously, I always operated, I ran SuperSID.py on a Windows computer, and everything was connected to the USB. This worked fine, and I got one trace on the power spectrum display plot. But when I tried with my LM7805, so I have an LM7805 supplying power to the sound card, supplying power to the Stanford preamp, and yeah, I always got two traces. Maybe I can show you on the screen. Yeah, can I share my screen?
Of course.
I've forgotten how to do this now.
And then you see a bunch of pictures, and you get to pick which one.
Right, I
Either
want
that
to
or
share. God. No, this one.
Oh, things are happening.
Can you see my screen then?
Ah, now we see a bunch of peaks. Yep.
Yeah. So, right.
Ooh.
The left-hand chart A
Oh.
is with my LM7805 supplying sound card and preamp, and this is with the configuration channels equals 1. And after a lot of chatting with Google AI, it's telling me that this is just duplicated. So it's set to 48 kilohertz. You have to correct me if I'm going wrong here. So the maximum frequency it can show me is 24 kilohertz. So the sampling rate is set to 48 and the maximum it can display is 24. I don't know why it's repeating it. If I set this
It
to
just sounds like a
channels
math confusion between those different frequencies.
If I
Okay,
set-
but you got something on the right looks much better.
Yes, so the real signal is the blue trace, and I understand the orange signal is just a kind of crossover shadow signal. It's thousands of times less power than the blue trace. So then I started the quest, how do I get rid of the orange signal? And it's all due to the fact that StarTech, I'm using the StarTech sound card, that's stereo, but the output from the SuperSID is mono. And I couldn't find any setting in the config that would switch off the unused stereo channel. So the blue trace is actually the right channel, sorry, left channel, which is the tip of the 3.5mm jack. And the orange trace is the ring, which is not connected in the Stanford preamp. So if I'm wrong, you guys correct me, but that's what I found. Okay, cut long story short, Google AI recommended I stick a 100 nanofarad capacitor in line, where is it? In line with the right channel, connect it to the left channel, and then both to the input of the SuperSID. Sorry, the output of the SuperSID, yeah. And the reason you have to put this 100 nanofarad capacitor is to decouple the power into the sound card, because apparently, I don't know, correct me if I'm wrong, but according to Google AI, the preamp, it can supply power to a microphone, and in order to decouple that from blowing up the amplifier, to decouple a power supply from the input to the amplifier, there's a capacitance in the preamp. Oh. Anyhow, it's C6. So if I wanted to connect my right channel to the left channel, I have to be very careful, because I could be putting power straight into the sound card and destroy it. So I put this 100 nanofarad capacitor in there, and hey presto, and now my traces overlap.
Okay.
So now
Yeah.
that's my workaround. It nearly drove me nuts trying to do this. So I think it's working properly now. So should be able to make some measurements. But I put on Google Groups a request if anyone else has had problems with Pi Zero and StarTech sound card, but I didn't get any. No one's responded yet. I think my workaround is correct, and I'll put it on the groups so people can check it out and criticize it if they think it's wrong.
Can I just say, Mark, that I mean, maybe this is technically what you're supposed to do to prevent problems, but for me personally, I just used a mono to stereo adapter, which is just something you plug in your mono and it goes out in both stereo inputs. It's just, if I take off the screen, I can just show you. I have to send a request. You have to. Do you want to unshare a second? I'll show you.
No, I did search for that, Andrew, but in the dialogue with the AI, it said be careful about doing that, because the input to the sound card. I'll get this right.
As I say, maybe technically the AI is right. I don't, but it worked for me
Yeah.
anyway. But I wasn't using a Raspberry Pi, just using a Windows.
Actually, Mark, your workaround is perfect. Yeah, you're basically combining both channels and decoupling any DC coming through that other channel. As a matter of fact, you could also put a capacitor in your other right channel, and make sure that there's no voltage going back and forth between either the sound card or your amplifier, and it would work just as well. So just like you have the one capacitor on the one channel, and it's just basically combining now left and right. You can put one in the. If you're worried about any voltages going back and forth between the two, between the input and output, you could put an identical capacitor on your left channel, and you would still get the sound coming through. And now you would have no problems with any kind of DC voltage going back and forth between the two. What I would suggest though is that I'm not sure what type of capacitor there. If you use an electrolytic capacitor. Mylar, perfect. That's exactly what you need to do. Yeah, and mylar is perfect, so it's not polarized. So your workaround is perfect actually.
So what's the chance that a SuperSID is going to generate a voltage? Then, Adrian, I mean, I don't know. I mean,
I don't know, but if you want to make sure,
myself definitely.
Yeah, because I don't know. Mark said that there's a voltage in order to operate a microphone. And I'm not sure how that works, but if you want to make sure you don't have any voltage between the two devices, the amplifier and the sound card, the way to do it is to decouple it with a capacitor. See, the capacitor will pass all those frequencies just fine, but it will not pass a DC voltage. So that blocks.
See, this is what AI explained to me.
Exactly.
So C6 is protecting any DC going into your sound card.
Absolutely. That's exactly right.
So I'd have to replicate that on the other channel.
Exactly. And you will not lose any signal, and it'll make sure that you don't have any DC voltages between the two inputs and outputs. So just replicate that same thing on the left channel. And so what you're basically doing is you're shorting your left and right channel together. See, that lower trace before was just bleed over on the channel that you had just open.
Oh.
Right? That red trace that you had initially, it's just bleed over on the open channel. And so that's why it was thousands of times weaker, because it was just a small amount of bleed over from whatever the electronics were. And so now what you've done is you've combined left and right channel together, which is, it's fine. You could have also just disconnected the other channel, gone into your cable, and then just cut out that wire, and then you would have lost that bottom trace. But this way it works fine. I mean, it shouldn't, it should be fine. And again, if you still have any worries about DC voltages perhaps damaging the input to the amplifier, but you can just stop that by just replicating what you did on the right, on the left, and it should work fine.
But for some strange reason, SuperSID, I can't. It always wants two channels. I tried.
Well, see, that's what.
Where is it? This one.
The doubling.
Yeah.
There, if it's just because what you're saying there is correct. The Nyquist frequency is basically the upper sampling, and then so in order not to get the distortion, then only the frequencies below that frequency are the ones that you're able to analyze. But why it's inverting, I'm not sure. I think it might be a sit.
You had a last slide there too, Mark. What was the meaning of the last slide?
Sorry.
On the bottom, you had a slide. What was the meaning of the last slide? It looks so similar to previous. Those last two.
Oh, they're just at different times.
Oh, that's fine. Okay. It seems to me that you've reached success.
Yes, I think so.
Yeah.
And I'm pleased that you've documented here for others as well.
I'd like to make a comment on the capacitor. When you use capacitors for audio coupling like that, mylar is very good. Mylar is good, and polypropylene are good, but stay away from any kind of ceramic. They can throw in odd distortions, and electrolytics are even worse. So always a mylar or polypropylene are okay.
Well, I use my friendly Google AI, and I asked it the opinion of my trace tonight, and it seems so happy. My SuperSID spectrum is extremely clean, blah, 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 blah. and it looks like the signals are identified correctly. So
Well, congratulations. This sounds great.
yeah,
The sound card
thank
is
you.
the DC voltage that's on that line. The sound card, is it the source of the DC voltage on that line?
He seemed to think it was from the SuperSID.
Well, that's what's confusing me. It seems like the sound card might be a logical source of this to try
Yeah,
to
so you're thinking
power
it's
the
coming over from the
microphone.
right-hand side there, Charles, huh? Okay.
Yeah, yeah, that's what I haven't run into that before, so I'm trying to make sure I start being conscious of it on sound cards if that's a new.
Yeah, I understand your logic. That would make sense for a sound card, trying to plug in a microphone that way. So, okay, good.
Yeah.
Thank you, Mark.
My next task is just to assemble it all in a. I've got a Hammond box, aluminium box, weatherproof box, and I'm going to put the antenna in a kind of low noise area. And I've got a 12 ampere hour lithium ion battery. I didn't realize it will only last about 3 days, so I'll probably have to buy a bigger battery. But my intention is to just put it in a low noise area and leave it going for a week, and then come back and take the results out with a hotspot. That's my plan.
One more question, Mark. What kind of power supply are you feeding the 7805 with?
With a battery, right?
Yeah, can you see it?
Let's see.
Yeah, big hunking
Lithium
battery.
ion battery.
Oh, it's a battery. Oh, okay. All right.
Yeah, and
I was
that
just curious what you were feeding into it. Yeah.
and the Raspberry Pi it's got a separate switch mode power supply and an element 7805. So I've got two LM7805s. One is just for the sound card and preamp, and the other 7805 plus switch mode power supply is just for the Raspberry Pi. And the Raspberry Pi and its SMPS will be outside of the aluminium box, the Hammond box. So inside the box, I'll just have the sound card and the linear power supplies. So
And what voltage? What voltage is your battery?
the battery's, I think it's 13.4.
Whoa. That 7805 must get pretty hot.
No, because there's a switch mode power supply in between. It drops it down to 7.5 volts.
Oh, I see what you're saying. Okay. All right. Well, I see. Yeah, no, 7.5 would be good. Yeah, you can't, yeah. Going straight from the battery to the 7805 is too much of a overhead voltage. But yeah.
I agree, but I
Okay.
did try that actually. I put everything on the 7805. The Pi, everything was running on it. And I measured the temperature of the heat sink. It went up to about 49 degrees.
Yeah, it would get pretty hot if you're running it much more over 7.5. Yeah. The only thing is that, well, you're helping things out as far as the bleed through, but the fact that the switch mode is going into the 7805, you're still carrying over a switching power supply input
Yes.
into it. But the 7805 also has a feature where it can reduce that switch mode power supply noise significantly. Ideally, you would have just a straight linear power supply going into the 7805. But I guess the next best thing is what you're doing.
But then it's only running the Raspberry Pi. So any noise regarding signals for the VLF, I won't have any noise. I just get noise back through the ground connection. Is that right? Because they've all got a common ground.
Well, no, if the switch mode is running into the 7805, right?
It's only supplying Raspberry Pi, nothing else.
Oh, so what's the input to the 7805 running your sound card and everything else?
That's the battery as well. So
but after the battery, you're running a switch mode power supply that then goes to the 7805, correct?
Yes, but I've got the battery has two connections. One is going to Raspberry Pi, switch mode power supply 7805, and the other going to a pure 7805.
So well, not sure I kind of see this. So directly, so the battery has one connection that's going directly to 7805. I don't get that.
Yes. It's got two connections. One is going to 7805 for preamp and sound card, and the other connection goes to the Raspberry Pi.
But you're saying that battery voltage was what again?
12,
Gentlemen, I'm going to ask this move
13.4.
over
Okay.
to email
All
at
right.
this point.
Okay, no problem. Sorry about that.
I have
Sorry,
a question.
When do you have a
Uh-huh.
question?
Does your information include photos of your hardware?
Yes, I can include some photos.
Well, I just mean for the future. I'd like to,
Yeah,
not for any questions. I'm just interested to see it.
sure.
And that's all.
Okay. It's my first attempt at making a circuit, so you'll have to forgive the terrible soldering. No.
It sounds great though, and I mean it works.
Yeah, I think you're making progress with your
If it-
adventure. Well
If
done,
it
Mark.
works, you can hire some critic to come in and reflow your solder joints.
Yeah.
Let's
Okay.
see. So Andy's talking about how he wants to come off later. He's still preparing his presentation, I think. I do want to get moving along here and get everybody in. Who else? I think that covers everyone on the east of the Atlantic. Thank you, Mark.
Okay, welcome.
And so who has a presentation over on this side of the Atlantic, on the US side?
Sure.
That was Steve, at least. And that's what I hear so far. Okay. We're going to give Andy a little more time. Sure. Steve, come on in here. Are you ready?
Yeah. You can
Let's
hear me?
see. What we got to do is unshare here. I think I can find a button. One of these. Oh, this one. Yeah, there we go. Okay. Steve, come on in here and tell us what you've been doing from San Diego.
Okay. I was motivated from my last talk in March to continue looking into the SARA archive. And on YouTube, there's just so much stuff there. And I came across another presentation, which I'll talk to in a moment, so which I can build on. On the left, you can see it. That was just a reference to the previous work where I was doing a lot of calculations manually. And so now I'm actually building on those concepts, but doing it with a different approach. I'm going to be following the analysis laid out in J.D. Krause's book, particularly section 610 of the simple adding and interferometer. And my inspiration is from the October.
Apologies, Steve. Sorry, Steve. Which book is that? Sorry.
It's J.D. Krause's Radio Astronomy.
Okay, thank you.
The 1966 version, although there are later versions. So, but it's chapter 6, section 10. Now, let's see if I can. There we go. So this was my inspiration. I'm going to try to build an interferometer building off of the approach that Ted Klein did. So as I wander through the great archives of the SARA YouTube, I came across this presentation almost 3 years ago from Ted, where he was doing some really impressive hardware stuff. And on the left, you can see a picture of the hardware he put together, which is a dual antenna. And he used something that he labeled the PVC zip tie Yagi, and it was ultra low cost Yagi antenna. I will encourage you all to go look at that video because they talk in back and forth on many of the concepts of a adding interferometer, which I think are very useful. And just before Ted's presentation is another one in the same YouTube video, is another one by Wolfgang, where he does what I would call the more modern interferometer, which is a multiplying interferometer. But this is kind of the older, simpler approach, which is an adding interferometer. And on the right side, you can see actually another little snapshot out of Ted's presentation, where he measures what I'll label as the interferometric antenna beam pattern. So that's actually, you've seen all these little plots of beam patterns where they have a big main lobe and they have some kind of smaller side lobes off to the side. Well, this is the beam pattern you get for the configuration of these two Yagi antennas spaced 2 meters apart, looking at hydrogen-ish line frequencies. And from this, you can read out, and Ted calculates in the upper right-hand corner, the full width half max of the beam pattern size of his individual Yagi antennas, his PZT Yagi antennas, at about 37 degrees for the beam width. And when you do an interferometer, you get an envelope function, which is essentially the beam pattern of the individual elements or individual antennas. So if you were to have plotted on the same plot the beam antenna pattern for just one of the Yagis, it would go up what I have labeled Yagi envelope and top off and down the other side, and it would be solid. It wouldn't be going up and down as the gold curve does. But those gold curves are essentially the side lobes, and the center lobe, or what interferometers like to call fringes, that's the main beam. And if you look at, and now use the same approach that Ted used to measure the Yagi half power beam width, you apply that to that central main beam, you will get about 3.3 degrees as the full width half max or half power beam width, which is about a factor of 10 improvement in resolution. So he's getting an enormous improvement in resolution by using an interferometer, but in this particular configuration, what I label as the side lobes are quite high. So the antenna is collecting not just where the main lobe is looking, but it is collecting out at about 5 places to the side at similar gain, not quite as much as the main beam, but similar. And so you can still use this like a regular antenna with a 3.5 degree full width half maximum beam size if your scene is simple, meaning like it's a point source with nothing around it that the other side lobes can look at, which is essentially what you're doing when you look at the sun, because it's, in this sense, this is in time, is essentially looking off to the side of the main lobe and then moving towards the main lobe and then back off to the side of the main lobe. So that I came across this and I was very inspired, thinking, wow, that is just impressive improvement in resolution. And if you can find a way to maybe deal with these side lobes, you could make something kind of fun and interesting and learn about interferometers. So this is what did was I put together this hardware configuration where I had, like Ted had 2 Yagis, I have 2 parabolic dishes, and I use the Discovery dish, 0.72 meters. And the thing that I changed, and you'll understand why later, was that I shrunk the baseline down from 2 meters to less than 3/4 of 1 meter. And so on the left, you can see the 2 parabolic dish antennas mounted on my air conditioner, since I only have a deck, not even a yard. So I couldn't get them far apart, even if I wanted to. And then the outputs of those 2 parabolic dishes have to be combined. Now, Ted did a very creative solution to that, but I did selected a different thing, which was a 2-to-1 Wilkinson analog combiner. And I saw Andrew had made a reference to a question on this topic of what is an analog or a Wilkinson combiner in reference to a paper done in the Eastern Conference. And so I went out, I had researched a Wilkinson combiner, and I purchased this one, which you can see in the picture to the left of center, and it was $10 off of Amazon. I'll come back and talk. I have a whole slide on this particular part because it's kind of interesting and different. And then, but I'll just keep going across the configuration at the moment. So after the two signals from the two dishes go into the Wilkinson combiner on its left, they come out as a single signal on a single coax on the right, and they go to a bias T, so which is the doing the exact opposite of what the last presentation, which is we're injecting a DC into the cable instead of trying to make sure that one is not there by putting capacitors. And the reason I put this part in is because the software-defined radio on the right has a bias T built into it, but it is of insufficient current sourcing capability to run two of the Discovery Dish LNAs. So instead, I put in this bias T, which blocks the bias T of the RTL SDR, the software-defined radio, and it injects its own. And in this case, I picked I'm sure is crazy noisy power supply to run this DC voltage, which is a phone charger. I just took my USB-C phone charger and I bought a pigtail cable and I attached it to the RF bias T as the DC power supply. So that ran me also off Amazon, about $15 for the bias T board and the phone charger I already had. Oh, and it was $15 for the board and the little pigtail cable to go onto the board. And then I already had a RTL SDR software defined radio, which was like $40. And we're going to be doing some measurements here, so I ran the frequency, center frequency for the RTL at two different frequencies, one where I'm going to be looking at the sun, which is moved off of the hydrogen line, and one where I'm looking directly at the hydrogen line for doing measurements. And I have the analog gain on the RTL SDR set to 50 dB, which is quite high, but that's what the combined gain of the Discovery Dish amplifiers and the RTL SDR need to get up into the good portion of the range of the A to D converter of the RTL SDR. Okay, so back to that new part. So on the left, you can see kind of a bigger picture of the Wilkinson 2-to-1 analog combiner. It's super simple. It has two SMA connectors on the left where you just connect the two dishes. And then out of those connectors, you can see is just copper wires, which are strip line paths, but they then come together at a surface mounted resistor. And this particular device, the manufacturer quotes very large frequency range, surprisingly large frequency range. And they also quote that the input and output impedance of this little board is 50 ohms. And that's good because the cables coming from the dishes are 50 ohm cables. So you want them to match. And going out of this and going into the input of the software defined radio, that's 50 ohms. So you want to keep the 50 ohm thing going. And if you have a input and output impedance of 50 ohms, it turns out that the resistor that you short the two inputs on the Wilkinson together with is 100 ohms, twice that value. Then they build two tiny transmission lines that they say that should be quarter wavelength in the wire. So it's different than exactly the wavelength in space. And that the impedance is not 50 ohms, it's square root of 2 times 50 ohms. So that's 71 ohms or something like that. And it turns out you can have these boards for all different kinds of input and output impedances. But this one is specifically for 50. And one of the magic that comes out of this is, unlike a lot of other dividers, which, by the way, the combiner and divider, same thing. But the fact that this is a Wilkinson method is it doesn't use resistors to divide up the power or combine the power. And that causes it not to dissipate much of your signal. And it gives you a crazily interesting characteristic, which is that the two inputs from the two dishes are, when they look into this board, they are isolated from each other by, the manufacturer says, a factor of 120 dB. which helps them not burn each other out as those two inputs from the two dishes don't fight with each other very much. And they say that the path length, the phase path, is about the same, to within 3 degrees on the two paths. So this is what their manufacturer spec said for this $10 little board. And so I pulled out my Nano VNA and I tried to verify some of these results. So one of the first things I do in the middle, the top little picture there, is me running a standing wave response test, because they give that this board on each of the inputs should have a standing wave response looking into it of less than 1.4, which is quite good. And it also means that since I'm using a Nano VNA that has a 50 ohm output, it also says that if I get anywhere near that 1.4 standing wave ratio, that the inputs and outputs from the board are indeed 50 ohms. So by just looking at the standing wave ratio, I'm verifying that it's indeed around 50 ohms. And and then when I did this test, the connectors I'm not using, as you can see in the two pictures with the Nano VNAs, I'm only using 1 or 2 of the connectors at a time. The remaining connectors are all shorted with 50 ohm resistors, which come with the calibration set of resistors for the Nano VNA. So I get really good square wave response 1.2, which is, approaching the ideal 1. And for both the inputs and the 1.3 for the output, I don't get quite 20 dB of isolation between the two dish inputs, but I get 17 dB, which is not bad. It's a reduction of their fighting with each other by about a factor of 50. So I thought, this isn't far off of what the manufacturer said they did, at least the parts I could verify. So I put that into the hardware configuration you saw on the previous slide. All right, so then I decided I was going to try out a new software tool for this one. And for this one, I chose SDR Angel. So some of the people on the chat are periodically using this. This piece of software comes with what's a radio astronomy plugin designed specifically for doing many of the things of hydrogen line observations. So in SDR Angel, you can see the kind of a screenshot of what it is, where I'm showing you 2 of the tools in the radio astronomy plugins. On the left a part of the picture, it shows you the planetarium tool. So it has many of the features of Stellarium, where you put in your longitude, latitude, what frequency you're looking at, the azimuth angle and elevation angle that your antennas are looking at, and it will, in real time while you're collecting data, produce this little picture below, and that's a galactic longitude, latitude representation. It also does the right ascension declination version if you prefer that, but this is the galactic version, and it's not a visible picture, it's at megahertz. And it will also present on there, you can see a blue line snaking its way through it. That is the path of your drift scan on the galaxy. And it'll put a real-time dot of, which I've labeled LOS for line of sight. That's where your antenna is looking at any given moment, and it tries to actually give you a readout of what the background temperature is looking in that direction in the sky. It will also note the location of the sun, which you can see also happens to appear on the drift scan path, because in this case, I'm actually intentionally scanning the sun to measure the antenna pattern, and it will show you the location of the moon. So if you want to try to do calibrations using the sun, or you're just interested maybe in scanning the moon and seeing if you can see that, the planetarium tool will show you where you're looking versus those things. And if you go up in the numbers above it and you change the elevation and azimuth angle, you point your antenna, it will real-time change the drift scan path to show you where does that path go through the galaxy, and when is it not looking at the galaxy, kind of thing, because those are useful for doing things like if you're going to calibrate the sensor for temperature, you want to know that you're looking at cold sky with not a lot of hydrogen in it. And on the right side, you see a radiometer tool, which is the full power tool, and it'll plot that out. And that's similar to some of the representations you can see in EZRA. They do a power versus time tool. Let's see. So I got the planetarium tool, radiometer tool, and it has the typical spectrometer tool where it'll give you, a spectrum of magnitude versus frequency. But in addition to that, I'll come back to that spectrometer tool later. But now the next thing so that was the hardware and software and the motivation. And now I'm trying to project what will an antenna pattern be if I build an interferometer where on the left, I use these discovery dishes and I will combine them in a pattern of dishes, which is represented in the center, which I call the dual monopole antenna pattern. And on the right is the interferometer pattern. So let's walk through that slowly. Back on the left, in my previous presentation, I manually measured the antenna pattern of the discovery dish to compare it to the manufacturer numbers. And in this case, I'm going to use the result that I got last time of 25 degrees for a full width half maximum for this dish. And I do a plot, and these graphs are done in just a spreadsheet. I do a plot of the antenna pattern as Gaussian. Many radio astronomers approximate their antenna pattern as a Gaussian because when you combine multiple patterns of the shape of your dish and the responsivity of your feed and other responsivity versus angle items in your radio telescope, the central limit theorem forces the result towards a Gaussian. So they just go ahead and use a Gaussian, and that's what I've used. Now, if you're going to do an interferometer, you've got these individual antennas, and then the separate thing to think about is I'm going to arrange them in a pattern. And this pattern you represent by the pattern of how you lay out a number of monopoles. And a monopole is just a hypothetical thing where the antenna sees the same gain in all directions. So you laid down the pattern you're going to put your antennas in, and you do some fancy math, and you get an equation saying if I had put little monopoles in all those places, I will get the following antenna pattern. And so right in white, I put the equation that comes out of the fancy math of doing two monopole antennas side by side, which is this kind of the simplest interferometer you can do. And then below that in the graph is the actual, just a plot of that antenna pattern. Now, what's interesting is, or you can see already, is that the dish is full width half maximum. The width of its antenna beam was 25 degrees, but the two monopoles just by themselves, which, see in all directions, they're full width half maximum of the peak at the center, the one at 0 degree angle, is 8.4 degrees. So it's already substantially different than the size of the dish, even though these two monopoles are placed almost the identical width apart as the diameter of that dish. And so that comes out of the math. It's it's not intuitively obvious when you think about it, but that's where it's kind of the basis of where the improvement in performance in interferometer resolution comes from. So now, if you take the way you combine the antennas you're going to use plus the pattern you're going to lay them out in on the ground, what you do is you simply take these antenna patterns and you multiply them together. So you take the blue curve on the far left and you literally multiply it point by point of how big it is versus angle with the red curve in the middle, and you get the red curve on the far right. And what you see here is it has the same kind of characteristics that I labeled in Ted's presentation earlier. It's got a central main beam, it's got side lobes, and it has not a Yagi envelope, but a dish envelope, because I used a dish instead of Yagis. And so if you use this little program then, or this little analysis to project the full width half maximum of that central lobe, that main lobe, it comes out about 8 degrees. So I'm projecting that for the hardware configuration that I have, which is the 2 of these dishes with 25-degree beam widths laid out in a little pattern of just side by side with 0.72 meter separation, I'm going to get a 0.8 meter, oh, sorry, 0.8 degree full width half maximum on it, which is dramatically less than the 25-degree beam width of the dish, of the 2 dishes I'm using. So this is, trying to get that improvement in resolution, which is one of the key performance parameters of a radio telescope, or any telescope really. Resolution and signal to noise ratio are kind of the 2 big ones. There are more, but those are kind of the 2 top line ones. So this is my prediction now that if I combine these 2 dishes through my Wilkinson combiner and now measure the antenna pattern by letting the sun go scan across my antenna pattern, I'm going to get something that's going to have about an 8-degree full width half maximum for the main lobe. And I'm predicting I should get side lobes that are not totally negligible, but they're around a factor of 4 less than the peak. Maybe a little bit higher than that, but somewhere right around there. Okay, so then what I did was I decided to use my new software and measure this again. So this is the radiometer tool. Again, on the left, you can see I decided first just to repeat my measurement of the beam pattern of a single dish. And so below it, you can see in green the measured power, and underneath the bottom scale, you can see is actually time. And SDR Angel allows you to pick your vertical scale and horizontal scale and the center of your graph by just entering those numbers in at the bottom, because it keeps, just like the other softwares do, they keep this kind of running power versus time. And it also has a Gaussian fit tool. So you click the button for the Gaussian fit tool, and then you tell it how tall you want the Gaussian to be, and you move it up and down until it matches the height of your measured data, and you tell it where 0 is, which you move up and down until it matches the 0 of the green data, and you tell it where the center is so that the peaks line up, and you tell it how wide it is in time until it matches the width of your measured data, and it'll pop out, calculate for you the half power beam width or the full width half maximum. And it does in degrees, and it knows, because of where you're looking in the sky and how long it took for this period to transition, it knows how many degrees it's actually moved, which is different if you look down towards the southern horizon versus looking vertical versus looking north. So it just makes that adjustment for you. And it came back with 25.8 degrees. And when I knock out the half degree for the sun, it's roughly 25-degree full width half maximum, which is consistent with the last measurement I did by hand. Now on the right, so I've replicated the individual dish performance from my previous presentation. On the right is the interferometer version, where the 2 signals are now combined through the Wilkinson combiner. And you can see the green, again, the green data, the green graph is the measured data. You can see the central peak with its higher gain, and you can see there are 2 major side lobes, just like the analysis projected there would be, and they are in the region of around a third to a fourth of the peak gain. And you go through the same Gaussian fit on the central peak, and it comes out at a half power beam width of 9.8 degrees. Take out the sun, it's 9.3 degrees. And you can now compare that to the 8 degrees I did with my analysis, projecting what it should be in advance. Then I wanted to do a measurement of the system noise. So in the spectrometer tool in SDR Angel, there's actually a calibration mode where you point the antennas at the ground and you hit the hot calibration, and it measures the green curve on the top. So I'm sorry, I'm referring to the left-hand single antenna case. And then you point the antenna at the sky and you hit the cold calibration button, and it'll plot on the same graph the response when looking into the cold sky. And it'll tell you things like how many dBs different from each other, and it kicks out a system temperature for you. So you don't have to do a calculation of it. It'll tell you what your system temperature is. You can now then combine that with the integration time. And unlike SDR Sharp, where you put in a number of spectra you want to average together and you time it to figure out how much time that is for your system, this actually calculates it for you. When you tell it how many spectrum to integrate together, it will tell you how many seconds of an integration time that is. One thing you do have to do manually is calculate the FFT, or the spectral bandwidth, in hertz, which is just the full spectral bandwidth divided by the number of bins that you have. Because those two numbers combined with the system temperature, you can now calculate the system noise, sigma system, which for the single dish with new hardware I'm getting, because I have the bias T in the path still, I get like just under 0.3 RMS Kelvin of noise. And I did that because I'm going to compare it to the signal to noise I get with the interferometer. I want to tell if the interferometer has both improved resolution and improved signal to noise ratio. And so on the right, you see the same calibrate, or different, I repeated the calibration for the configuration of two of the dishes stuck through the combiner. And it goes through and calculates the system temperature, and I do the same calculation below and get about 2 RMS Kelvin of noise. So it's, in this point, yes, the interferometer is less and it should be less, but the real important thing is the signal to noise ratio better in the interferometric case than it is for just a single antenna, which you would expect to be when you add two antennas together. You'd expect to get improved performance in some way. So the next thing I did was I measured a hydrogen line signal. So this is on the left, I did it with a single dish first, and I looked at the location in the sky of the right ascension and declination, which, by the way, every graph on the spectrum, the SDR Angel presents, it puts the right ascension, declination, galactic longitude, galactic latitude, azimuth, and elevation right at the top of the picture. So you're never kind of wondering where and or what you're looking at and trying to remember, when I took this picture, where was it looking? So this, you can see a big green spike from the hydrogen line data. And because you do that calibration before to calculate the noise, it isn't just oh, here's some numbers to calculate the noise thing. The vertical scale on the left now is, you have a drop-down menu and you can have it in dB. But now, because you've done a calibration, the drop-down menu allows you to simply make the graph in temperature, in Kelvin. And so the delta temperature for this graph on the left is 49 Kelvin. And if you combine that with the noise that I calculated for the single dish on the preceding chart, looking at this location in the sky, it's a 169 signal to noise ratio. And by the way, this is a resolved section of the sky. So that does matter. What that causes is, it means that when you measure the signal, delta T peak, it'll be roughly the same for the interferometer and the single dish, because if you look at my preceding presentation, I showed you had to scale down things if they don't fill the aperture. But in this case, it fills both beams, either the single dish or the interferometer, so you measure the same peak temperature difference. And so on the right, I did the same thing with the interferometer. I got very similar, within 10% for the delta T peak. I'm not exactly looking at the same place in the sky because I couldn't line it up exactly the same, but I get a higher signal to noise ratio. So I will also mention that SDR Angel has if you like a spectrum, there's a button, you just hit it and it shoots it out as an image file. So you can then store it as a picture, drop it into a presentation if you like or not. And in addition to that, let's see if there's another button, since it stores every spectrum as it goes along. It doesn't just keep the current spectrum. There's a button you can hit and it'll make a video of your spectrum playing one right after another kind of thing. And so there's on the left is that it puts it out in a presentation. Since I work on a Mac, it puts it out in a file form, the video in a file format that is animated PNG file, which Macs won't play. So I ran it through a file format converter to do an MPEG video, which is what these two little videos were. And so this is now my last slide. So for this adding interferometer project, these are the results. I have demonstrated a resolution improvement, beam width reduction, of about 2.7, narrowing the 25-degree beam to 9.3 degrees. I have demonstrated that the side lobe gain can achieve is significantly below the 50% main lobe, 50% of the main lobe gain, so that they're not overwhelming the performance of the main lobe. I've demonstrated a sensitivity improvement of about 1.4, with the signal to noise ratio increasing from 169 to 242. And that, it turns out, is almost exactly what you would expect by getting double the collecting area with two antennas added together rather than one. These values for the beam width and the measured performance parameters correlate well with a small difference in the full width half max of about 16% and a 2% difference in the signal to noise ratio off of an ideal square root of 2 improvement. And that's it. So if you have questions or comments, I would be happy to entertain.
That's magnificent. You came up with a whole bunch of new ideas for us. This is great. You had that fancy PC board in there for $10, whereas I just took two wires and shorted them together, not even shielded. So a great improvement. I need to explore that. That's cool. And we got to learn more about this SDR Angel. This looks great with all kinds of buttons. I've been afraid to explore it, and you were brave and wandered the wilderness and came back with stories. That's great.
Brave is the right word. It is complicated.
It's got lots of knobs.
It's not as straightforward as, say, Ezra or SDR Sharp. It takes dedication to work your way through, and it has, I will describe as, relatively poor documentation.
Oh dear. Oh my. Okay. So what we got to do is come up with a beginner's introduction of what knobs to push with all that detail. Yeah, we need another pioneer. Is there a like Google groups or email forum to talk about this thing? You would think so.
I didn't think about that. I turned to AI several times. It
Oh,
seems to
okay.
have good answers I use the built-in to Mac, whatever that version, whatever AI that is. And so that's where when I got stumped and I didn't know, how do I do this? It actually walked me through several things.
Good, because AI can read the manuals for us. Edward says he's used it. Did you want to come on with audio and tell us more about it?
Yeah, well, not too much to tell about SDR Angel. I've used it just 1 or 2 times for demos out in the field. So I also have a MacBook Air, and I like this a very lightweight laptop, so I can easily carry it to a presentation, for example. But at first I had a problem that I couldn't do live demos of the hydrogen line because Sharp won't run on the Mac normally. But as SDR Angel does natively, so once I got that working, it works fine. So, but I haven't really experimented too much with it beyond just some live demos, to be honest.
Anybody online, have they been a pioneer and explored SDR Angel? I just hear echoes. Okay, excellent. Well, Steve, thank you so very much. Other questions for Steve, please.
I have a quick question, Steve. Do you know what kind of, if you separate the dishes more, do you know what kind of relationship there is between that and the beam width reduction offhand?
Well, it's reciprocal, of course, but let's see. Actually, if you look at the equation, when you go back to the video, you can actually look at the equation. It's a complicated, a cosine of a sine of, and I'm trying to remember if the d over lambda or lambda over d parameter is inside the cosine, but not inside the sine. It's not, because by the way, the beam width of the side lobes changes as you go off axis. It's not a straightforward, simple thing. So that's why I did it's fancy math and didn't put up any discussion or talk about it kind of thing. The one thing I'll say is the J.D. Krause book mentions specifically, first off, they often talk about full width first zero as opposed to full width half max. So they go to the first zero of the antenna patterns, which is about twice as much. But it says that the full width first zero for an interferometer is half of the full width first zero for a dish. And I looked at that and I go, but the dish is the same width. Why would it do
Hello, my name is Ed. I'd like to.
Oh, sorry, my fault. Apologies.
Okay. So, but I think the closest I could come to understanding why that might be the case is a dish. It has those ultra high resolution interferometer pairs as the strip right out at the edge of the dish at its maximum thing. But it also has pairs of interferometers, multiple of them. You can kind of conceptually divide up your dish into little pairs coming all the way into the middle. So you have a whole range of different interferometers adding together and the different resolutions. And the pairs that are close to the middle make very broad patterns. And so they kind of wash out the zero to further from where it would be than for just an interferometer. So it's because the interferometer's missing the stuff in the middle. That's a really bizarre statement.
I think there's also another factor maybe coming into play here, and that's the dish illumination. Like if you have your like antenna at the focus of the dish, it is never like going to fully illuminate the whole dish.
Right.
So you have like typically you're like illuminating the edges of the dish much less. Otherwise, like you have a lot of spillover,
Right.
getting all the thermal radiation from the ground. So you can, in theory, I think, narrow down the beam of the dish by illuminating it more completely. But this comes at the cost of thermal noise from the ground, from spillover,
Yes.
which will then degrade your sensitivity. So it's a trade-off.
Yeah. You're going below what actually a dish could do because, as you're right, because you can't just stop the reception of the feed right when you hit the edge of the dish, which is what you would want to do for all maximum performance. Because it takes space to fall off, you have to actually start falling off early, and you're turning down the gain on the highest resolution parts of the dish, which are the edges. So Krause goes through like a convolution argument over the whole thing. So but it was too complicated to try to introduce here.
Neat. Okay. Other questions, quick? I want to recognize Liam. Liam, are you there? Welcome to the group. I hope this was quite an introduction today. I'm kind of impressed. Liam, tell us where you are and why you're here.
Yeah, is my mic working?
Your
It
sound
is
great.
not. All right, good. Yeah, I don't know. I've been interested in radio astronomy for a while, I think. Hey, don't mind me. I just gotta grab my laptop. That's my bad. Bye. But yeah, I've been interested in radio astronomy for a while. I started off by ordering an SDR kit 4 that I had here, and I guess I didn't do much to with it until about a couple weeks ago when I picked it back up. So I built a radio telescope. I haven't used it yet, but it's a Horn telescope for 1420, which is the hydrogen line. So I've yet to use that with SDR Sharp and the IF average plugin found. So I think it's just I've always been just science and stuff has been interesting to me, and this is just a new path, especially after getting my radio license. And I think it's really cool, and I just want to keep working on it and possibly pursue something of radio astronomy as a career in the future, such as working with the NRAO or those telescopes and such.
Magnificent. We see your ham license is Kilo Mike 7 Echo Yankee Romeo. And did you tell us where your home is here?
Yeah, I located in Tucson, Arizona.
Excellent. Lots of clear skies down there. We want to make sure you know about our email forum. I'll put that in the chat here just in a moment, where we can't stop ourselves. We talk about this forever, all times of hours, all from both sides of the Atlantic and all. So welcome, welcome. Sounds great. We're eager to see a picture of what you have in time. Thanks very much. Perhaps another new name. Oh, we got a couple here. Let me try to pronounce it. Enajkahadka is the way I'm coming up with here. Oh, good. Your mic's off. Tell us more about you. Where are you?
Hi, can you hear me?
I hear you now. Oh, there we are.
Yeah, okay. Yeah, I joined this SARA for like maybe like more than 6 months, almost a year now. But like, so okay, just telling myself like I'm a graduate student here at West Virginia University. So I do radio astronomy research, but not much like technical side. I do more on the algorithm side. So I was like trying to get involved because we just do the research and we don't know like how the instrument works and all these things. And I wanted to learn it, but like graduate student life is always like you have a lot of works to do. And so I always miss the meeting, but this time I just was determined, okay, like I don't want to miss this meeting. At least like I want to get started. And so that is how I'm in here. So yeah, that's me.
Excellent. Help us with your name as well. Is that
Yeah, so
we
I
see
just
your
like
screen name, and it's probably two names there.
yeah, it was just like when I just signed in, first name and last name just kept together. So my first name is Anos and the last name is Khadka.
Magnificent.
I'm originally from Nepal, came here for my graduate study and I'm doing my research. Yeah, so
And you found our YouTube videos, I think. And I hope you know about our forum where we exchange emails and yak forever.
yeah, actually like I was there in SARA conference, Eastern Conference at Green Bank
Oh, I'm sorry, but I
last
wasn't.
year.
I was online. So, okay.
Yeah, okay, yeah. Last year I was there at the SARA conference in Green Bank, and that is how I knew about the group and everything.
Magnificent. Welcome.
Yep, thank you.
Eager to find out what you're up to lately.
Yeah.
Another visitor is Laris. Laris, are you listening to us? Can you tell us more about you?
I guess I'm a visitor. Yes, I was actually at the conference this year. But yeah, I mean, I've been a member of SARA for a few years actually, but it's been more on the sidelines, watching the videos and reading the journal and whatnot. But now finally have some time to actually start playing with stuff. So right now I'm just listening and watching, and came back from the conference with a lot of ideas. So I'm sure there'll be something coming out soon. So yeah.
Well, I apologize. Welcome. This sounds great. Jamie, are you in there? Do you hear me? Come tell us more about yourself. Maybe not. Okay, we understand how this works on. Let me move on to any other presentations today. We are certainly filled with information today, but it's taking a while. Presentations.
Well, I've got something, Ted, if everybody's finished.
Okay. Otherwise, we're going to get quick updates from folks. Andy, if you're ready, I think it's your turn for a presentation, and then we'll go around for other quick updates. You had your chance to.
Okay, well, this is just a bit of fun. I think Jack and I are the only two people who actually went in person to Green Bank. I don't know, is there anybody else online that went? No? Okay, so really, if you've never been, this is just to show you what you missed, really. So let's start off with, it's just a set of photographs. You can see that, Ted, can you? The SARA Eastern Conference, 1st to the 5th of August.
We see a black screen with the text. Looks great, nice and full.
Hey, excellent. You can hear me okay. Can you hear me without problems?
We hear you, we see it. Looks great.
Brilliant, fantastic. Okay, let's get going then. So obviously this was a couple of weeks ago. I see everyone else must be a bit too tired to attend this evening. Those that went, I'm not surprised. It was quite a hectic time. So this is my quote of the trip that somebody gave me. It was my first time in America. So I put with that. Very interesting trip indeed. Absolutely great time. So Jack, who's also online tonight, when he heard that I was going to this conference, he contacted me and said, right, I'm going to pick you up from Dulles Airport in Washington, and I'm going to take you down to the conference. I'm going to bring you back. And then my wife, Mary Beth, and I are going to put you up for a few days so that you can go and see Washington and New York City. So they really made it into a special trip. And the first thing that he did is what would have been a 4-hour trip along a highway. It took me a more meandering 8-hour route so I could see a bit of the countryside through some national parks, particularly Shenandoah National Park, and something that's reasonably famous called Skyline Drive, where you have these things called overlooks where you can look out across this valley below. Absolutely beautiful. And at one point we had to wait for an adder to cross the road, which was also a bit strange. Another picture. Two of us there. Eventually we got to Green Bank Observatory, which one thing that stands out, it's in a radio quiet zone. Then when you're speaking to the staff there, you sort of realize what that means. It's a big question for you all just to contemplate. Is it child abuse if your teenage child cannot use a mobile phone and go on to social media because you're in a radio quiet zone and you have to go and do activities with them instead? And then I discovered that Pocahontas wasn't just something that Disney invented. When I realized we're in Pocahontas County and that she was a real person. And then we started to see some incredible historic telescopes. This was going to be a real part of my trip for those two weeks and a bit. You know, actually seeing not just telescopes, but the actual things that did all the amazing discoveries. So this is Jansky's, which you could see out the front. And then before we did anything else, there's Rich there showing, I've got eggs over easy. I worked out what eggs over easy are. On the left-hand side, discovered this thing called biscuits and gravy, which is that splodge thing on the left-hand side of his plate, which actually doesn't taste too bad. But with a strange name, slightly stranger breakfast. Having said that, on that sort of first full day, we didn't have the conference because we arrived at the end of Friday, so we had Saturday. And there's a chance for me to go for a walk. And I don't know whether you know that as part of your membership of SARA, you have access to a remote telescope at Green Bank, which is 20 meters in size. It's a good way of showing off to your local astronomy club. If they think having a remote telescope in Arizona or Spain is a great idea, well, you know, they've only got maybe 100 millimeter telescope. You've got a 20-meter one in a great radio quiet zone that you can access. And not many members do. We now have thousands of credits available. So learn how to use it and get going is what I would say. Sorry, it's my mobile phone, apologies. And then walk down quite a long distance gets past telescopes. And this one, the 140-foot telescope, enormous thing, which has probably made more important discoveries than any other telescope, radio telescope in the world, I suspect. And then, of course, there's the 100-meter Green Bank telescope, absolutely enormous. A couple of pictures. All these pictures have been taken by me, so it was a real sight. And for those interested in hydrogen line, at the front there's the Ewan telescope. This is the actual telescope that he made and was the first guy to detect hydrogen in the Milky Way. And I ended up doing some talks. There is me doing that. And you're in Drake's Lounge tonight. So here's the actual original and best Drake's Lounge, which is a room at Green Bank, which we've met up in the evenings. And there's a chance for people who bought along bits of kit, go outside and see those different bits of kit in action. Obviously, a bit of hydrogen line being detected there in the middle. And They asked for a volunteer. I tend to always volunteer for most things, a bit idiotic, I know, but that's me having my body temperature measured using the 40-foot dish. There's another thing that we can use at Greenbank that still uses old style pen and paper to plot out its results. So each time it goes to on there, moves slightly to the right, that's me standing on a stool. Off is when I got off the stool and got out of the way of the telescope. Obviously just something to remember the place by. Okay, so we went back home and back to Jack and Mary Beth, who were absolutely fantastic hosts. But I was able to see Jack's new build in progress, which is his 1.5 meter dish that he's building here. And here's his workshop. I made the mistake earlier today, Jack, of showing my wife this workshop. And as you might guess, her first reaction was, look how neat that is, i.e. yours isn't. Why is it not as neat as that? But he's building the various bits and pieces there for his 1.5 meter telescope, including top left, a really neat drive system. I still had a chance to go and see New York City and Washington. So here I am in New York City. I did get a chance to walk up, at least to the pedestal on there on Lady Liberty. And even got my photograph taken with a couple of New York cops who were very nice people. And then there are 2 space museums in Washington. This is back to Washington now. One in the center, which is the Smithsonian Space and Air Museum. And then it's also another part of the Smithsonian group, which is called the Stephen Udvar Hazy Museum, which is out near Washington Dulles Airport. And that was a place I really wanted to go to. We had this rather strange looking robot that I believe has been taken up on the ISS. And this was the guy that I really wanted to see, the Discovery space shuttle, which was big. Pretty much everything in America was big compared to the UK. Usually it was very big compared to the UK, and Discovery was nothing different. But it was amazing to be able to get there and actually see the real thing. Those little people at the bottom on the left-hand side give you an idea what sort of size we got here. And then the other bucket list item I had was I wanted to go and see the Declaration of Independence and the Constitution. So there's me next door to the real thing. Wasn't very legible, but it's still there. There we are. Photographed and photoshopped a bit to make it a bit more legible. And a few sites. The National Monument at the bottom right there was a bit memorable because, oh, I haven't got it here. While I was there, there were a couple of helicopters came over and landed in the White House grounds. So I did ask one of the policemen around who was shooing us away from that direction. I said, what was it, the president? And he did give away the game and say, yes, it was. So I saw the president either coming in or going out. And then I got to see some real life things there in America. Here's the Home Depot. I wanted to see these, but as I used to do a bit of amateur telescope making, and all the books used to point to American hardware stores, which seem to stock so many useful items which we can't get in the UK. So it was nice to go and see the real sort of places where these things are, including this guy here selling Halloween buckets. I did notice that the Halloween trick and treat buckets sold in America were substantially larger than the ones which the kids here carry around. Clearly, American children do expect an awful lot more to be given to them at Halloween. And you also have some rather mighty tools on offer, including this drill here, which I only just about managed to pick up. And then the one thing I'd missed by not being in the UK, of course, was the solar eclipse, which is around about 90% here in the UK, with 100% down in Spain, which Eduard here managed to get down to. But nevertheless, I did go and join Jack at his Astro Club, and we had some neat views of the eclipse and also a very nice prominence coming off the side there. Here we are, there's the eclipse. And us on their 14-inch STT. That's their club observatory, sorry. And I went to the Natural History Museum, which if you ever get a chance is phenomenal, with the one in Washington. That's a full-size big whale behind me. And the most incredible meteorite collection. When no one was looking, I put my hand on this one. I reckon if it'd been around for 250,000 years, stuck somewhere, it probably was going to survive my hand. And then again, going back to the sort of the real things, here we go. We've got the Freedom 7 capsule. I forget exactly, was that Gemini or something like that? And then we got Neil Armstrong's actual spacesuit, sorry. These are sort of things we don't have too much of in the UK, which it was wonderful to see them. Another thing, oh, sorry. It's me with a picture with Jack's 100-year-old mum. She just turned 100 while I was out there. And one of the things my firefighter daughter was a bit surprised at was this picture showing fire engines of many colors. We only get red ones. Actually, we stopped by the fire station, and the lady came out and said, "What are you doing?" And I said, "Oh, I'm just trying to take a picture of a fire engine because my daughter's a firefighter." And as a result of that, Jack and I got asked inside, and we got the guided tour of the fire engines and the ambulance and a good chat. And I ended up with free patches and all sorts to bring back to my daughter. And there we are, the patches. And during the flight on the way out, I actually conducted, to come back to astronomy again, I actually conducted some experiments with muon detection at altitude versus ground using one of the Pico muons from the UKRAA. And that worked. And so I was able to present that data at the conference itself as a talk, which is really neat. That's just the badge from the conference. And there's just a picture of Jack and Rich there, just to finish, with the 100-meter there in the background. So that's me done. Thanks very much.
That was a fun tour of what you did on your summer vacation. That's great. I need to get to some of those places myself.
Thank you. No, it was incredible fun. Incredible fun.
I'm glad Jack took such good care of you. Well done.
He did, and all our compatriots here in SARA also did a phenomenal job of looking after me at the Eastern Conference as well. No, it was just great. I say to anybody here who's never been to the Eastern Conference, I'm assuming the Western Conference is as good, just I've never been there. But if you get the chance there, go there and see Green Bank and take part, just do it.
Well, magnificent. We've had so many presentations. Who else now, please?
Yeah, I have some small things to show from actually my trip to France and Spain for the Eclipse, but also some radio astronomy related things over there. So
let me just preface, yes. So if anybody else has a presentation, we want you to speak up. This is going long, but this is okay. We got tape. Edward, tell us all about it, please.
All right, can you see my screen?
We see a nice big shit. No, it's like a reflector.
Yes, it is. So this is the reflector of the great radio telescope, the Grande Radio Telescope at Nançay in central France. So this was one of the stops along the way to Spain. I did a little road trip with my brother and a friend. Nançay is I think the biggest and oldest radio observatory in France. And this is one of the parts of their main radio telescope. So this is a Krauss type radio telescope, a similar design to the Ohio State University's Big Ear radio telescope that discovered the WOW signal, but that one is dismantled, while this one is still operational. So what you're seeing here is a big flat reflector that can tilt, and it's reflecting the radio waves coming from the sky up to this next part over here. And now this is not working. This one. Yes. So this is a spherical reflector. So this is focusing the radio to a central point. It's not a parabolic reflector for some reason. So this is another picture of the spherical reflector on the south side. So just to give you an idea of scale, so this is about 300 meters long and 35 meters high. So this is at the central point. It's a bit of a blurry picture, but you can see here the horn antenna which is at the focus. It's on rails, so it can actually move along to track the sky for about an hour or so. So there's another picture of the flat reflector.
If we go back
this is at the side.
Show us the horn again.
Interferometer.
Show us the horn again. Where's the input? The top part? Yeah, with your mouse.
I think it's the lower part. The top part just houses the receivers.
So,
but it's a bit of a complicated construction. Like there's multiple reflectors inside as well, but I don't exactly know how this functions.
Well, me neither. Okay, very good. Thank you. Carry on.
All right. So this is another instrument over there. This is an interferometer. So this is the radioheliograph. So they use this interferometer setup to image the corona of the sun at around 400-ish megahertz. And this is another shot from one of these dishes where you can see the actual feed. So you can, that's all for Nançay, I think. And now I'll just quickly skip through to the solar eclipse. And just a moment. There we go. So this was, so I drove to Spain and, or we drove to Spain and we met up there with Robert Lucas, also from SARA. I don't know if he was on earlier tonight, but we stood on a hill near Soria where we met up and we viewed the solar eclipse together, which was really nice. So this was before first contact. This was just after first contact, so you can see a tiny bite out of the sun. And then this gradually progressed, of course. This is a shot through the telescope. So I brought the telescope with the solar filter so I could actually view it as well. So this was during totality. So Robert is the guy in the red shirt just below the eclipse sun. So it was really a great experience. Like there were a lot of amateur astronomers from, well, all over Europe and even outside of Europe on this hill, as well as a lot of local Spanish people who came here to view the eclipse. This was during totality. So you can see the solar corona. What was also really nice, it doesn't show up well in the image, but you could really easily see it through the telescope, is the prominences. So these were like the sort of the pink parts around the eclipse sun. And that was it. So one final cool thing was that the sun was still partially eclipsed when it went under. So that was also really nice to see. Anyway, that's it. That's all I had to show for today.
Beautiful pictures.
I enjoyed that. That's fun. So many fun things going on this month. Okay, now, folks, be brave. You're going to follow those presentations. Come on, tell us what's going on.
I got nothing.
All right, Wendy spoke up. Let's start just going down alphabetically, and I guess we probably should keep moving right along. Adrian and then Charles Dennis. Adrian, what's the quick news? Adrian is muted.
Yeah, sorry, I couldn't find my microphone there.
All right, Adrian's still muted, or I clicked on him.
Okay, how's this?
Now we hear you. News.
I've got maybe a little brief sort of update type stuff that I could maybe talk about. Okay, let me see if I can share.
Ooh, a presentation then. All right.
Let's see.
We're filled with news today. This is good.
Let's see. Where am I here?
We see things happening. Ooh, nice big blue screen. Go ahead.
Okay, let me see if I can get this in presentation here. Let's see. Just have a hard time finding this. Hit F5. Yeah, F5 doesn't. Oh, there we go. Okay.
This does look good.
Yeah.
Carry on.
All right. Well, I've got some kind of brief stuff here. It's kind of an update from some of the stuff that I presented at the Eastern Conference. So this is an observation of a object W44, which is a supernova remnant that I had done some initial imaging raster scans on. And so this is kind of the raster scan that kind of brought me onto this. And this is the central object up in that top square is 4. And this particular raster scan, and this is all done with the Green Bank radio telescope, so I don't want to go into a lot of background here. We don't have a lot of time. But the raster scan in this particular observation did this kind of a strange sort of addition towards the bottom of the actual raster scan, which would normally just be kind of a square. And you can see that there's this kind of an object that's kind of peeking out from the very bottom there. It's not that it wasn't supposed to be there, but I didn't know it was going to be there. So it intrigued me. Just what the heck was that thing? And was it even real? So I decided to try to see if I could figure out what that was. And so again, this is the kind of an image of the actual supernova, the actual target that I was trying to observe, the W44, and it's kind of an optical picture of the circular thing with a superimposed, the kind of pinkish thing. It's kind of the radio emission of it. And so I did further scans on it just to kind of zero in, but this one didn't quite catch the other object. So you see in the central part of it, the W44 image of the actual supernova remnant. And then the diagonal line is actually the galactic plane. So what you're seeing there is kind of the emission from the galaxy, which is in the background of the object. And so I tried to move this around a little bit and was able to kind of slide on down and get both objects in. So the top one, the top object then is again W44, and then you see that bottom object, which is quite bright and quite prominent. And so with a little bit of snooping investigation, whatnot, I was able to identify it as another radio emitting object called W43, as you would go, 44 and 43. And so they're both of them together. Now, W43 is a completely different object. These two things are not the same. W44 again is a supernova remnant. W43 is it's a starburst star forming region, probably about the most active in our galaxy, which I was not aware existed, and it just happened to be that close to W44. And again, as I said, W44 is a supernova remnant. And you see the emission from it because the supernova shock wave is impacting kind of some adjacent cold hydrogen clouds. And so it has a lot of synchrotron emission that's coming out of it. Again, W43 is a completely different object. It is a huge, gigantic cloud of gas, hydrogen, which is actively condensing into numerous new stars. And so here's some pictures of that. On the left, you see kind of an optical view of it, which there's not much you can see because it's really hidden behind a lot of dust in the galaxy. So it's just kind of really obscure. If you go down to infrared, you begin to see a little bit of structure. And if you kind of do some radio analysis, you see all these little circles, and these are all features, is what they call them, that are probably just young stars that are being formed, or at least in the process of being formed in this region. Again, this hydrogen cloud collapsing. So there's a lot of hydrogen here. So I thought, well, wow, that's kind of an interesting thing. What's the difference between these two guys? And so again, here's the spectra of the combined two objects. That should be W43 up at the top. And so you see two different frequencies that I scanned with the green bank. So the top one kind of centers around 718 or so, well outside any hydrogen line. And then the bottom ones, you can see the very, very prominent hydrogen emission around 1420. And so I thought, well, it'd be kind of interesting to kind of separate these two features out and see what these two objects kind of look like. So here's kind of what that is. And so what I did is I went ahead and I don't have all the bells and whistles in my computer to do the analysis. So I got the FITS files into, I believe this was the Google Gemini AI, and asked it, well, draw pictures of the FITS files doing some various filtering. So on the left, you see both hydrogen and what's a lot of the emissions coming out of these guys, which is continuum emissions. So again, there's two main types of emission from objects besides thermal, and that's called Bremsstrahlung or breaking radiation, which is also called free. And then there's synchrotron emission, where you have high energy fields of magnetic lines and high energy electrons that also radiate. And so what you're seeing then is a combined emissions there from again the 1420 and outside of that 1718. And then the central image there is essentially taking the hydrogen line out of the image. So you can see that the brightness, so what you're seeing is mostly just continuum. So it would either be, again, this free or synchrotron emissions. And you can see, and I know the scales here, you can see, for example, in the combined, it's up to about 30 Kelvin. In this filter now, where hydrogen has been taken out, the scale drops down to about 12. But yet the W44 now almost seems equivalently as bright as 43. So that's really what's happened is W43 has dropped an incredible amount of brightness in terms of the image. So now you're seeing them be more or less equal. And what's really just mind-blowing is if I now take those signals and I subtract out the hydrogen line, and W44 just disappears. It's gone. And what you see there on the bottom there is W43, what you would expect to be emitting a lot of hydrogen, because again, it's a gigantic gas cloud, that hydrogen that's collapsing down into new stars. So that I thought was really interesting. And again, it just shows the completely two different types of objects, W44 being a supernova remnant. There's very little cold hydrogen, hydrogen there. Any hydrogen there is probably H2 ionized, plus synchrotron emission from the high energy magnetic fields and so forth. And yet the W43 being a mostly hydrogen having a lot of H2, HI, and mostly free emissions, then having a fairly significant amount of signal, which is quite obvious then for this particular rendering. So anyway, it's just kind of a quick update. I didn't know what this object was during the Eastern Conference. Figured out it was W43, and then just a really remarkable sort of distinction of just how different these two objects are when you look at the various emissions that are coming from it. So anyway, that's pretty much it.
Thank you, Adrian.
My
That's
unshare
cool.
button.
Even more to explore. Let's see if I can help out there.
Yeah,
I push this button.
Great. Thanks a lot.
Excellent. Next up is Charles. Charles, what's going on?
Well, I'm in the middle of a power outage, so the best thing I could say is I'm testing all my UPSs, and my dish is still observing and calibrated during the storm. So power's out and everything's still working. I got 49 minutes to go before I run out of battery. So carry on.
Well, you are prepared. Maybe that cuts down the RFI. I could see all those monitors turned off behind you.
Yep.
So there's hope. It'd be interesting to measure before and after during this power outage. Good luck. I'm working down the alphabet. Who have we not chatted with? Dennis is next, Donna, and then we're down to Bruce.
Okay. Hey, Ted, thanks. This has been an amazing session. I couldn't say anything for fear of embarrassing myself. These presentations have been amazing. Thank you.
Very good. That was short and quick. We're down to Donna, who we haven't heard. I'm just going down the alphabetical list. Then Bruce and Preston.
Good
Donna.
afternoon, everybody. I've been a member of SARA for quite a while and never seemed to get my act together on Sunday afternoon. So I just thought I would sit in here and see what was going on. I found everything to be extremely interesting, and I hope to join again. So thanks very much.
Donna, I think you were at least online for the conference. Is that right?
Yes, we were.
Yeah. Okay, good. Excellent. Well, keep coming back and telling us what's going on. Sounds good. I'm working my way down to Bruce, Preston, and then Rick, please.
Yeah. Hello, had a good time at Green Bank up there and got back. And the week after getting after Green Bank, I was going after trees. I had a large oak tree that had grown up and was keeping me from taking my fold down ham radio tower down. So I got my grandson here with me. So that killed the week. So the tree is down out of the way, and now I can start on my tower, but no radio astronomy stuff, just a lot of, hanging around in the trees for a bit there. So that's about it from here. Bye.
Thank you, Bruce. Preston, I guess, please.
Okay, I've just got a question, and if I've missed something, I'm sorry, but is anybody mapping the methanol masers at 6.7 gigahertz?
6.7 gigahertz.
There were, Preston, the door lottery that we had at the Eastern Conference. There were a couple of devices that were part of that, which some people were lucky enough to get, because the problem with 6.7 is the difficulty in getting appropriate kit to do it, and there isn't a single sort of LNA/filter that you can buy like the Sawbird that'll do the trick. So you need to, basically there isn't a commercial one that's exactly right, so you need to get a few bits and pieces. So that's certainly an important part of it. And this is where my brain goes completely befuddled and I don't understand it. But Adrian would know. Adrian, what does the Terrasat do? Because you were kind enough to send me one as well. And remind us what the extra bit is we need to go with it.
Sure. Okay, well, the thermostat is basically a converter, or at least parts of one. So when you have an input amplifier, and then you have basically a mixer, and then you have the ability to introduce a local oscillator signal there that will then shift down that 6.7 megahertz frequency down to something like, I don't know, 1.5 or 1.6, where you can then feed that into a regular SDR. So what you need for it, number one, you need a local oscillator. So again, that's a 6.7 gigahertz. If you do the typical super heterodyne type of thing, if you feed about 6,000 megahertz into it, then you'll get an intermediate frequency of about 1.7, or rather 5,000. So you need a local oscillator that'll feed the signal into it. And it does have a front end amplifier, but you might still need some additional, as you said, amplification and filtering, because there's adjacent cell phone signals and so forth. Wi-Fi is kind of up there, around the 5 gigahertz and so forth, that 5 gigahertz Wi-Fi band. So there's a couple of bits and pieces you need for it. But the person really to talk about this is Dimitri. Dimitri has actually done method monitoring at 6.7. And
Okay.
if you look into the SARA forum and kind of check out 6.7 megahertz or Terasat or something like that, you'll run across some of the posts that Dimitri did. As far as I know, he's the only one that's actually done methanol monitoring at 6.7. I think Edward might still be around, and he's done it at the other methanol band, which of course it's a lot easier to get equipment with because you can have U-type TV LNBs to reach that frequency. But yeah, the drawback against 6.7 is the ability to get that frequency and get it down to where it can feed into a SDR that you can. I don't know if that helps.
Yeah,
The basics on it.
I was wondering where to find an LNA for it.
Oh, LNAs are not a problem. You can get wideband LNAs that'll go, 100 megahertz to 10 gigahertz. So you can get wide bandwidth. Again, what Andrew was saying is if you want to filter a bandwidth out of that, so that you can get a filter up in front of that so it doesn't get saturated by all the other crud that sits around 6 gigahertz. So the LNA is not a problem. There's lots of LNAs that you can get that'll work. Again, the Terasat is sort of the converter. It does have LNA front end on it, but you might need a little bit more boost. I think it might only have something like 17 dB or something amplification on the front end of it. And typically, of course, you need something more like along, upper 20s, 30 dB gain to really begin to see something like a mason. So again, the problem is just more, and you can home build. Actually, if you go back and look at some amateur radio type construction articles, you can use copper pipe end pipes or the end caps for copper pipes that make tunable filters. You basically kind of drill a little hole in the top of the pipe cap, put some probes underneath it, use that top hole to put a brass screw into it, and then you can tune those into a band pass filter. So you can build your own sort of band pass filter around 6 gigahertz. That's not a huge construction problem if you kind of follow some of the earlier ham radio type construction articles. And again, the LNAs are available. So the most difficult thing would be something in the converter version, where you then need essentially the core super heterodyne aspect of it. It's some kind of a little bit of a front end, which you can then compensate if you have an LNA, a mixer that you can then pipe in a local oscillator signal that'll give you an IF down somewhere where SDRs can analyze the IF. So it's a little bit more complicated than hydrogen because you're not feeding it straight same frequency down to the SDR at 1320. So it's kind of similar like when you use those LNBs, for example, to view either the 22 gigahertz water masers or the 12 gigahertz other methanol masers. You need a frequency converter to get you down so that your SDR can then do the analysis for the signal. I don't know if that helps.
Well, thank you for your advice. Anybody else have any for me?
Have you done 22 gigahertz?
No. I've only done 1420 megahertz.
Okay.
And Joe.
And as Adrian said, the 22 gigahertz is potentially better. I'm trying to do that myself at the moment. I've had one go and I didn't detect it, but it may well have been a pointing problem on my telescope or something else. I hate to offer Eduard without him offering himself, but he was brilliantly supportive. He's a person to beg about getting some help on 22 gigahertz. Really knows his stuff. But I don't know how much time he's got. But maybe he could run a group session for everybody.
But I'd like to see somebody really, and maybe something only like Dimitri can get up there to those frequencies. But what is it, up around 90 gigahertz or something like that? The carbon monoxide emissions, which are used quite extensively in radio astronomy. And boy, that just seems like almost really out of reach for amateurs getting equipment up to up there 90, 100 gigahertz. But that would really be the most challenging, I think, kind of possibility for any SARA member. Anyway.
Thank you, Preston.
Thank you. That's what I had. Thank you.
Rick has been patiently waiting. Rick, what's the news down there? You're working with DSES, the Deep Space Exploration Society, with their 60-foot dish.
Yep. Well, I went down there Friday. I hooked up my big trailer and hauled that down there and unloaded our second 3.2 meter dish for an upcoming interferometry experiment with a matched pair of 3.2 meter dishes. So our next challenge is to design the interferometry experiment, in particular decide what baseline to put them on and how far apart we want them to be, because we're going to put them on concrete. So we need to decide up front where we want them. So, but anyway, I took that down. So we now have two 3.2 meter dishes ready to go up. And we also, of course, have the 30-foot dish that's down there ready to be erected. And we have sufficient donations to begin those projects from a donor who donated a great deal of money for that purpose. Also, while I was down there, a team led by Roger took a great deal of time and effort and finally found out what was wrong with our local area network and got that up and running. And we managed to use the network to collect some necessary data for some more engineering projects. And I was able to install the latest version of the software I presented at the SARA East conference, which is now radically grown beyond what that presentation was. So I'll have to put together a new presentation. But it does everything from planning to execution of pulsars, magnetars, and drift scan work. So I didn't have time to test out all of its new features because of all the other activities we were doing down there, but I left it running, collecting drift scan data, and it's probably got 2 partial days and a full day of data. So in a couple more days, I'm going to take the output of it and put it into the Easy family of post-processing. This replaces Easy Call, and if all goes well, it'll show that we're doing the right things. So maybe more to talk about next week. Over.
Well, that's a whole bunch then. Rick, let's talk about Easy, Ezra, and stuff if we need. Maybe converting data format. So we'll see. Good. I think we've touched everybody. Please speak up. Any final comments or someone I missed, please?
Photo of my radio telescope I can show, if that's okay.
Oh, good. Show us pictures, please.
All right, let me just share.
Liam.
Yeah.
Oh, yeah.
That's all. That's just fun.
How wide across is it now?
It's about 22 inches.
Okay. We see the shiny side. It's shiny aluminum stuck to what? Wood or cardboard or what?
Foam board.
Oh, great.
Foam
Okay.
board.
And have you connected it up yet?
Yeah, it's kind of in the background, but you can see a little bit of coax draining down, but it's not too easy to see. I haven't done a real scan yet. I will do that probably today soon. It took a while getting SDR Sharp to cooperate, so I'll have to with the IF Averager plugin since I don't know what's going on, but I was able to get it, so we'll do a 1420 scan sometime.
Excellent. We want to see results next time. That'd be great fun.
Yeah, definitely.
Andrew enjoyed a nice horn like that, and he found out sometimes it gets filled with water. So good luck.
Yeah.
Liam, where is the probe
Yeah.
in this picture?
What do you mean, the LNA or anything?
Where the cable comes into.
Oh, yeah, it's so if you focus on the center, that's the feed horn, and it's shielded with some more foil and whatnot, and there's like it's just behind the telescope at the main center.
Does it point out into the?
Yeah, it points out. Yeah.
Not from the side.
I think so. I don't know I think, yeah.
So there's kind of a little can at the bottom of that great big horn, and from the side is a little probe that monitors the electric field at that point.
Yes.
And where is that probe in the picture?
You can't see it, but it's behind the telescope. I'll have to.
It's down in there. We should be able to see a little stick, but contrast is missing.
Yeah, it's hidden.
Right, though.
The axis of that probe, is that along the line of sight direction, or is it orthogonal to it?
It's along the line of sight, I believe.
I think it's probably sticking in from the side, like pointing up.
I think that's what it should be doing, but as best I can see the picture, it is what Liam just said, which is it's pointing straight out of this picture, basically. Is that right?
Yeah. Yeah, pretty sure.
Yeah. Liam, if you stop sharing a second, I'll just share a picture and you can see what Steve's getting at. Okay.
We're concerned about that direction.
There we are.
That's his equivalent picture.
Well, it's not mine, just off the internet.
Okay. But Andy, you're saying there's a stick coming down from above.
Well, that's what you're talking about, isn't it, Steve?
Yes. Yes. And which is not coming straight out of the horn, but orthogonal to it from the side. It's poking in from the side.
Yeah.
And that makes a difference.
And the length of the horn matters. So the length of the little stick coming in the monopole matters, and how far away it is from the back of the rectangle box at the back matters as well.
And Andrew had a cartoon view of a diagram of the back of a horn too at one point, which
oh dear, yeah, okay,
shows the geometry. And if the probe points straight out of that picture, it's not going to pick anything up, or at least I don't think it does.
So I took a screenshot of what you had there, Liam, and zoomed way in, and yeah, we're concerned that it's pointing at our noses.
Right.
And we think it should be pointing up towards the ceiling, for example.
Side to side, any one of the four sides it could come in at, but
I don't recommend the bottom.
I'm trying to think, or will it work?
Do you have a cartoon?
We've just never seen a design that way. I guess the distance from the reflection is what matters to maximize the E field.
The electric field direction has to point along the wire of that probe. It has to be in the same, so that it can push electrons along the wire. And I don't think the electric field will be going vertically or horizontally, but I don't think it comes in and out of the picture.
Anyway, we're sharing a little feedback, Liam. Good luck. It'd be fun to hook it up and see what happens and tell us about it. But we were expecting the probe to be pointing up towards the ceiling, as an example, as opposed
So
to
would
pointing right at our eye. Good catch, Steve.
so would that little copper piece and that's supposed would you rather have it being on the top and then going down instead of going straight up
That would be fine.
or on one
Pointing
side?
at pointing at the floor or pointing at the ceiling be great.
Yeah. Andrew had
Those
a
two are
cartoon that
equivalent.
showed it very clearly.
Yeah, I'm just trying to find it at the moment. I'll be just a second to find it.
Andy's quick on his keyboard here.
Yeah, yes. Plus, it was very illuminating.
I think Andy's
graphic.
wandered the
There-
whole web
Amazing
looking for
idea.
these things before, so he's been.
There
But this is
there
great.
is a-
Yeah, we like. Otherwise, we like the dish. Yeah.
There is a type of feed where the feed comes out just like Liam has, but it doesn't stay straight. But it does a 90-degree turn somewhere above that back. So it doesn't have to directly come out of the side. It can come out the center. But then what you do is you fold it over 90 degrees. So then it essentially would have the same orientation as if it were coming out the side. A lot of TV.
Yeah, exactly. For big TV dishes used to have that.
Right.
And
Yeah.
mine had a little motor that would rotate it so you could have different
Precisely.
polarization.
Precisely. That way you can just use the single feed for multiple polarizations, especially with satellites where you don't necessarily just have horizontal or vertical, and you might need to go through several angles of the rotation. That's how they work. Yeah. So theoretically, he could just take that thing but I'm not sure the dimensions and extending out and then making that 90-degree turn to form the quarter wave, what that would be. But really, the best thing is just to come out the side like normally it's usually done.
Right. So, I mean, so that shows where you normally see it coming out. I mean, I tried putting it at the bottom to start with because I was concerned at the top that it would. You might get water going into the coax, which is problematic here. But I put the bottom, unfortunately, then collected water in the rectangle, which then stopped it working. So I've now changed it so it now comes from the top.
So Andrew, in and out of this picture is the same as in and out of Liam's picture. Only the big end of the horn is into this picture, and his was out of the picture.
Yeah. So there's the big end there, where you can see at the small end. And if
you can zoom in for us, can't you?
Yeah. There we are. So zoom out. So here we are. You can see so there's the horn on the right hand side. This is actually and here you can see the basic idea box at the bottom, which is your waveguide, and then you've got a horn which is to collect the radio waves and basically direct them down into the waveguide. And you can see on this diagram here where the monopole goes in through 76.2 millimeters. This is SETI League plans, this particular one. They're saying from the back. I'm not sure if I entirely agree with that, but still it seems to work. And the basic idea that you've got a chassis connector with a bit of something stick out the side. I mean, we've had lots of discussions on this group before about what constitutes, and also on the Hydrogen Line group on Monday evenings, about what constitutes the best stuff to use. As shown here, sort of 2 millimeter copper tubing seems to perform better than anything else, but I've certainly got these things working very well with a straightened paper clip. Just cut so the length of that matters, and that distance from where it comes into the back matters as well. Those are the two things when you look it up are supposed to be important.
Liam, you'll find that this group always has lots of opinions, and so we're not sure we always agree. We always encourage exploration. So keep exploring, but we're delighted with what you've done there. This is fun. Come back and tell us what happened. Thank you.
So, Liam, do you have a way to get into the forum now?
Yeah, I believe I should. Yeah,
there's a link in the chat today. So
yeah, I have.
That's one entry door at least.
Because I know when I first started in SARA, all of a sudden I had been in SARA for 6 months and I got a lot of material I didn't know I was supposed to have. So sometimes it takes these guys a while to pull away from their real life and get you what you need. So don't be afraid to get on the forum and make sure you have what you need from the group, okay?
We encourage. Thank you. We
So just
appreciate the pictures. That's fun.
yeah, so just to be
Anybody
clear,
else have comments as well, please?
I would say that if you did a little looking at the cantenna puts a probe in the side at a measured distance from the back. And it's well detailed if he does a lookup for cantennas and looks at some of the designs. And that's how that little dipole needs to work in there, is to be in line with the RF that's coming in.
So that'll give you some of the dimensions he's thinking.
Be it cross purposes, so that it's going to intercept the RF rather than having the signal going down past the end of the probe.
Wow, so many things today.
Yeah.
Excellent. I think we'll call it there. Thank you so much, folks, for hanging in this long. Lots of interesting subjects. And now you got 2 weeks to figure it all out and tell us what's going on in 2 weeks. See you at let's see. The end of this week on what I call Friday, Australia calls it 9 a.m. in Sydney, is going to be the Australian Drake's Lounge. So hope to see you then as well. Until then, have a wonderful week and go catch those electrons. Thanks, everybody.
Photons.